The law of sines is one of the trigonometric formulas that expresses the relationship between the lengths of sides and the angles in a triangle. Let's prove it briefly. First, let's consider the case of an acute triangle. In the yellow right triangle, the sine of angle A is the ratio of the height h to the side C. In the blue right triangle on the right, the sine of angle C is the ratio of the height h to the side A. Let's verify this for obtuse triangles as well. For the acute angle C, the sine value is sine pi minus C equals h over A. Since sine pi minus C equals sine C for both acute and obtuse triangles, the sine C equals h over A. From the first equation, h equals C times sine A. And from the second equation, h equals A times sine C. Therefore, these two relationships are identical. Dividing both sides by AC yields the equation sine A over A equals sine C over C. If we construct a height h from vertex C to side AB, and apply the same method, we obtain the equation sine A over A equals sine B over B. Hence, the law of sines is established. Let's consider a few problems. The first one involves the angle side case. Given angles A as 35 degrees, C as 45 degrees, and deducing angle B as 100 degrees, we substitute these values into the given equations. When calculating proportions, it's convenient to use the cross-product property. Multiplying diagonally and dividing both sides by sine 35 degrees allows us to find the value of side B. The approximate length of side B is 17.1696. Using the cross-product property in a similar manner on the right-hand side equation, we can find the length of side C, which is approximately 12.3280. Moving on to the second problem. It falls under the angle side angle case. Given angles A as 38 degrees, C as 47 degrees, and deducing angle B as 95 degrees, we substitute these values into the equations. Using the cross-product property, as before, we multiply diagonally and divide both sides by sine 95 degrees to find the value of side A. The approximate length of side A is 12.3602. Similarly, using the cross-product property on the right-hand side equation, we can find the length of side C, which is approximately 14.6830. The third problem involves the well-known ambiguous case, often referred to as the SSA case. In the yellow right triangle, the height is given by b times sine A, which, upon calculation, is approximately 12.8558. As mentioned in textbooks, when the relationship between the height of the triangle and the given two sides is A is greater than h and less than b, two possible triangles can be formed. The blue triangle represents the second case. Now, let's solve this problem. Applying the law of sines to the first triangle, and using the cross-product property, we rearrange the equation to find angle B. Using the inverse sine function, we calculate that angle B is approximately 58.9870 degrees. Angle C is then found by subtracting angles A and B from 180 degrees, yielding approximately 81.0130 degrees. Now, let's find the length of side C by applying the law of sines and using the cross-product property, resulting in a length of approximately 23.0494. Now, let's consider the second triangle. Here, angle B can be easily determined as 180 degrees minus the size of angle B in the first triangle, approximately 121.0130 degrees. Therefore, angle C is approximately 18.9870 degrees. Applying the law of sines and using the cross-product property, again, We find the length of side C to be approximately 7.592. Thus, we have determined all the unknowns for both triangles in this ambiguous case. The fourth problem is also SSA case, similar to the previous one but with a slight difference. In the yellow right triangle, the height is given by b times sine A. And upon calculation, it is approximately 12.8558. However, if the height of the triangle is greater than the given side, A, a triangle cannot be formed. As discussed earlier, the SSA case involves pre-assuming the height through calculations and determining how triangles may or may not be formed based on the relationship between this height and the given sides. As seen previously, the SSA case can result in two possible triangles or no triangle at all, depending on how the height compares to the given sides. Of course, there are cases where only one triangle is determined. Please carefully examine the relationships presented. See you next time.